Hello, welcome to Engineers Ireland and to the second half of trigonometry. Now this may be either one long talk or I may divide it into two talks, but we're basically going to be dealing with the second chapter of trigonometry. This is a section that gets a lot of bad press. A lot of people find this quite boring, but in reality, once you get through school and you're off into college and you, let's say, are dealing with physics or something like that, you find this stuff to be one of the most significant aspects of the mathematics that you'll have in your toolbox, and you'll be able to deal with some really interesting questions simply based on this stuff. If you haven't learnt it well for your Leaving Cert, you run the risk of making your college life more difficult, and that would be a complete sin, because you're meant to have fun as well as learn while you're in college. So then, the second chapter, what is it covering? It's mainly covering a few basic identities and a whole load of the compound formulae and the double angle and half angle formulae, and it'll deal with the sine and the cosine rule. Okay. Anyway, up to this, for junior cert and really in chapter 1, you've been dealing with the trigonometric functions as ratios of sides. For example, the sine of an angle was the opposite over the hypotenuse, and you would be forgiven for thinking of it as just being ratios, but in reality trigonometry is completely generated out from the unit circle. Okay, and when you look at the unit circle, you actually find that sine and cos are lengths. So let's start with that. Okay, the unit circle has a radius of 1. And we'll say, we'll look at a rotation here, an angle of A. Now from the tip of the radius, parallel to the y-axis, we can draw a line towards the x-axis. Now the first thing you'll notice, well, first off, the radius is 1, as you know. We have now just formed a right angle triangle, and any time you see in your maths course a right angle triangle, you should immediately think of Pythagoras. And that will get you to your first identity. But let's find out where cos and where sine are now at this stage. That length there is sine. That's sine A. This length here is cos A. So then, rather than being a ratio, sine now is a length, and the length relates to a hypotenuse, which is the radius of 1. So once you've got a hypotenuse length of 1, you finish up with a vertical side there, which is the sine, and the horizontal side, which is the cos. And Pythagoras tells us immediately now, generally in the books they'll give you a different method for working this out, and you can follow it too. It's the length between 2 points, and fundamentally that just depends on Pythagoras anyway, so why not just call a spade and write your first identity, this guy, and state it by Pythagoras, because it's immediately obvious, because we're dealing with a right angle triangle. The second identity is formed from this one. But there's a few interesting things that come out from this, and we look at it in a diagram in a second. If we divide across, and divide across would mean all terms, by cos squared A, we get At this stage we have to get introduced to two new variables. These are tan of A is equal to sine A over cos A. And the next one then, see, between sine, cos and tan, they're your three basics. The next three, which are the inverses of these, are the important thing to recognize in them is the third letter. There's an S on this one. There's a C on this one. And there's a T on this one. So, there are other ways of learning these things off. They're just my way, and I'm sure a lot of other teachers and other people around the country use it, but I find it by far the easiest to remember. Just the third letter tells you which particular inverse it is. So now we're in a position to continue with this. Anything divided by itself is 1. And if we have x squared divided by y squared, that's the same as x over y squared. So what we get here is tan squared A. And now we can replace. So that's the second identity. The interesting thing about both of those is you can actually be asked those to prove them on the Leaving Cert. They're very short. So okay, why is this interesting? Well, it'll help. This drawing should help you understand why tan is called tan. Okay, so let's have a go at this. Now then, that's quarter of a circle. It's the first quadrant. If we draw the tangent right here where it hits the x-axis, let's just draw it straight up the way. That's the tangent to the circle on the x-axis. And now we'll draw what we've had already. Radius is 1 here. Now let's extend out the radius so that the radius now runs all the way out until it just touches the tangent at that point there. Okay, so the tan for this point here is now touched by extending the radius. This is our previous Pythagorean triangle. So we know this is sine. This is cos. Cos A continues out this far, and we know that that length is 1 because it's the unit circle. The interesting thing here is we have two similar triangles. They both have right angles. They both share the angle A. So the other two angles are the same. And what we know from junior cert is when we have similar triangles, if we can find a ratio for any side, that ratio for an equivalent side on the two, that ratio holds for the other two. Now the interesting thing is we do know one of them, and they're the ones down here. So let's start. Cos A is to 1. So we've got cos A in the unit circle triangle, and the smaller triangle is to 1. And we're saying if cos A is 1, then 1 unit here is 1 over cos A. Okay? So we know, and that is equal to sec A. So we're saying something that was 1 in this, the longer version is going to be sec. So that length there, the extended radius until it meets the tangent at the tangent to the circle at the x-axis, that extended length is sec of a. Now then, what about the sine one? When we had, where we had the sine in the first one, now in the ratio, remember, you'll notice from this line, what we're doing is we're dividing across by cos. So now we'll get sine over cos, which is tan. So sine A is in ratio of sine A over cos A, which is tan of A. That's now telling us that this length here is tan of A. So then, that second identity is in fact just another triangle, and that triangle is similar to the first triangle, the one that this identity belongs to. All we've actually done when we divided across by cos squared A is we've divided across by a constant, and once you divide something by a constant, all you're really doing is you're scaling things. A square is a square, no matter how big, small or indifferent it is. The quality or the character of it doesn't alter just because you decide to make the square 1,000,000 times bigger. It doesn't change what it looks like. The sides will still hold the same ratios. Technically, these are the same thing. But the interesting thing is they actually belong to two triangles, and they relate to the unit circle, as we've seen here. So tan of A can be seen to be related to the tangent to the circle at the x-axis, the positive x-axis. Okay, let's move on. Before moving on to the double angle formulas and the other formulae, the books are very good at starting you into the idea of solving identities or proving identities. And obviously now at this stage we have a small number of relationships, so the type of problem we'll get now is not going to be particularly hard, but the principles of how to solve the problems can be seen from it. The one in Rowntree's book is a nice simple one. Now, I think you can recognize that one of the reasons he'd have given this question is just so as to get you used to what cot is and sec is and cosec. You're getting all three of the reciprocal functions. The basic rule about these things is that you actually work on one side. Now, generally we refer to that as the left-hand side, and this is the right-hand side. Now you get to choose which one you go and play with. The idea is that you play with one side and look to form it into the shape that's in the other side. So we might be looking to get cot A plus 1 over cot A equal to, actually get it equal to, sec A and cosec A. The second rule about this is, having tried one side, if it's not working for you after maybe 5 lines or something like that, you'd say, I don't really see where it's going. You stop. There's no room for being a hero on this and continuing on, because in your exam time is important and you can't waste it. Haven't got a certain distance down, if it isn't clear to you, what you do is you take the other side. So you may have started with the left hand side and then you move across to the right hand side and you try to turn it into the left hand side. So we're saying the left hand side here, let's simplify it. we know so that's all we've done. You'll notice again, I always do my keep it clear stuff, the kind of thing, just to keep the mind clear. It always gets pushed over to the right hand side. That way you can check out the little thing that you're dealing with, and then when you migrate it back, you still get a very clean problem that you're working on all the way down along. Okay, so this is crying out just dealing with little fractions. Now, again, it's a very nice problem that he has presented, because now you're supposed to recognize this. One of the great keys of dealing with trigonometry is looking and recognizing when you get your basics in trigonometry, almost all of these type of problems that you get is the simple exercise in observing and recognizing something that you know already, a basic friend. Now we know cos squared a plus sine squared a is 1. That was our first identity. Okay, so we'll say that is equal to 1 over and 1 is 1 by 1. So, isn't that equal to? Now then, remember the C belongs to that guy and the S belongs to that guy. That's not a difficult job. But the idea of this example is not to show you difficult mathematics, it's to just introduce you to the principle of how to deal with these. We just dealt with the left hand side and we got it equal to the right hand side. The proofs of the compound angle formula are on the exam. Now, they're actually very easy. Once you get the first one requires just a little bit of thinking. The remainder of them just fall to you. So let's start with them. Now, in general, it's always best to draw a drawing and keep your life free of having to imagine what things look like. I spoke too soon there. We have 2 points P and Q. Now we're dealing with the unit circle here. What can we say? Well, P, which is related to the rotation or the angle A, is cos A sine A, and Q is related to B. Now what we're trying to find out is the relationship of an angle, a different angle, which is A minus B. And we're going to be looking, and what we're trying to prove is the cos of A minus B. That's your starting point on all of these, okay? So we're looking at this middle angle here. The interesting thing is we are going to just use two very simple equations that you've been basically using since junior cert. And those two equations are going to have us hunting for one particular thing, the length PQ. And when we find it in each of these two methods, we'll equate one to the other, and the thing just falls, and we get our answer, okay? So, PQ, that's the distance from that point P down to that point Q. Now we know the relationship for this. We know that the distance between 2 points is the square root of something, so why not save ourselves a line and talk about the square of it, okay? All we have to do is multiply these out now, and we will find that our first identity will kick in again for us. So let's see. What we'll notice is that we have these, and they are 1. And they are 1. Okay? So what do we have now? And that's one expression. You'll notice already, because you know what the cos of A minus B is, you notice that we have the guts of it in here. So we're well on our way. So now, what's the second method that we can find PQ by? We can use the cosine rule on this. So let's have a look at that thing. Oops. That's our second expression. And because both of them are equal to the PQ squared, we can set one equal to the other. So we can say, now, that implies that 2 minus 2 cos of A minus B is equal to That's very simple. All we've done is looked for that twice. We've looked for it in two methods. We've looked for it by way of the difference between 2 points, and the points obviously are the P point and the Q point. We've also looked for it by way of the cosine rule. What's the length PQ in the cosine rule? And we found the second method, and you just set one equal to the other and the answer comes out. Now believe it or not, this is the hardest one of these, so it'll be a big relief to you to see how easy the rest of them fall. Okay. What we know is plus 1 is equal to minus 1 multiplied by minus 1. In other words, I can replace that plus by a minus minus. And again, let's return to our drawings. Still the unit circle. So what's a minus angle? The plus one is pretty obvious. We will call this, just for the moment, we'll call that B. And going down the way, the opposite direction, it's minus B. We can replace this line here by what we found out already, because we're dealing with a minus. So we're saying it's cos A, cos of minus B, plus sine A, sine of minus B. All we've got to do is to find out how these things relate to the positive angles. And we find it from this drawing over here. We know in the unit circle that this is cos of the B angle. And interestingly enough, you can see it's exactly the same as the cos of the minus B angle. So what we can state is cos B, cos of minus B equals cos of B. See, they're both positive, okay? It's the same piece of the x-axis that you'd measure if you're getting the cos of the B or the cos of the minus B. But what about the sines? Well, that's the sine of B. The sine of minus B is down here. It's the same length, but it's negative. So and now we can sub that in. Now, by the way, you don't have to draw this over here. I'm drawing it just so as to keep the basics clear in your mind, because once you have your basics clear, you can deduce most things yourself. It would be a pity that if you were to proceed without just clearly understanding this little concept, okay? It makes the next step absolutely obvious. Cos of minus B is just cos of B, so we're happy. Now, what we have is sine of A by sine of minus B, and sine of minus B is minus sine B. So I get minus sine A sine B. That's it. Whole thing done. That's not a problem. So, they're the two cos ones. Now how about the sine ones? How does this work? There's only one little trick to this, and the trick is to understand something that you've been dealing with for quite a long time, and we just look at it by way of the simple Pythagorean triangle. We look at we'll call that angle A, and we call that's a 90, so I know that's 90 minus A up here. What we know is that the sine of A in the unit circle relates to that side. On the unit circle again, this angle up here, that side relates to the cos of it, okay? So we're saying then, sine A is the same thing as the cos of 90 minus A, and you're saying so it's complementary angles. So that's all we're going to deal with, just complementary angles. So here's sine of A plus B, and we're saying this sine is equal to the cos of its complementary angle. That's an easy step. Now where do we go from here? Obviously, if we've introduced the thing like this with the brackets around the A plus B, we want to split this up, okay? So we will say, because we're not likely to get further by just using it in the same form it's in now, so we'll say that's equal to and now what we've done is we've turned the sine of an A plus B into the cos of an angle minus an angle, and we know this latter part. Now then, cos of 90 minus A, can't we change that? And the sine of 90 minus A, we can change that also. There are these two things down here. That's nice and easy. Yet another one of them. It's very important though for you to remember, not just for these particular derivations, but to remember how simple the little keys are to solving these, because as you move on and you get to the further on ones, in remembering these keys you will find that they actually turn up again. And what you should be able to do is allow your mind to convince itself that trigonometry is actually very straightforward. Once you've learned the few basic keys how to manipulate these things just using complementary angles or the negative angles, then it'll start to make sense to you, and then it should become easy. Now the sine of A minus B is carried out in a very similar fashion. It's very easy to work out, so there's no sense in my working it out. If we look at tan, I will just look at one of these. Let's say, what is tan? Well, you say tan theta is equal to sine theta over cos theta. So we'll say, isn't that equal to and both of those we can expand because we know their expansion. Now, we know that we're hunting for a formula for the tan of A plus B. And we know that we want that formula to express the tan of A plus B in terms of tan of A and tan of B. In the exact same way, when we were dealing with the sines and coses, we wanted them in terms of, simply in terms of sine A cos A, sine B cos B. What we'll notice, or we can notice very quickly, is there's a cos here and there's a cos here. We know that tan is the sine over a cos. So if I divide this whole expression by, if I multiply it by 1 in the form of something divided by itself, and if that thing allows me in these individual terms to divide by the cos's, that'll then give me a nice handy tan expression. Over here we'll see, in this first one, we'll say sine A. I'd love if that was a tan of A. That means I have to divide this by a cos of an A. And I also must divide it by the cos of a B, because I've got a cos of a B in here. So this first section here, I'd like to be able to divide by cos A cos B. This second section, I've a sine B. I'd like to be able to divide by a cos B, because then I'll get a tan of B. And I also have to divide by a cos A, because I want to get rid of it. So that whole expression I can multiply by 1 in the form of something divided by something, and we found out what the something is. It's cos A cos B is what I want to divide through. Okay. Again, a very easy one-trick little pony solved this thing. You'll notice that we've spent a lot of time on real basics here. The key to trigonometry is knowing your basics. These expressions here are extremely useful. There are many versions of them, and some of them are pretty easy to work out, okay? But more important than that, the real issue is to be able to look and see what's there. For example, and this one is again given, and it's a good example, given in this textbook. We're asked to prove that identity. Now you could become the hero here, and you could go and expand that. You could also go and expand that, and you get lots of little terms all over the place, and you can play around with them and spend a nice amount of time, which goes tick 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 away in your exam. But instead you can do something different here. We could say to ourselves, in our mind, we could say, this thing here, I could, for argument's sake, I could see that as another angle. I can name it anything I like, okay? Let's just call it Z for the moment. So technically, and I'll write it over here, and this is the left hand side, remember? And that's the right hand side. So technically we can say the left hand side is the same as and that's something we can identify. We know what that is. Cos cos plus sin sin. So very simple. I like the ways he's put that question in here, because there's an important lesson, and the lesson is rushing in to try and solve a question isn't your best path. It's always best to look, interrogate the question, look to see what you can recognize in there. Now it's pretty clear here, because we're dealing with the compound angle formula, that when we're given identities to solve, that we will find that we should be able to see a version of a compound angle formula. This one here is very nice, and often when you look at these type of problems, if you get a real telltale like an x plus a y and an x here, in other words what's out here is part of what's in this one here, start looking for a compound angle. Okay, now these naturally lead on to double angle formula, and double angle formula is basically saying that instead of talking about an A and a B, we're saying B is the same as A. So what happens when we're looking at cos of two A's, sine of two A's? They are fundamentally a special case of the compound formula, and they're straightforward, okay, and they just come out to be they're straightforward. Just replace B with an A in the equations you worked out already, and these pop out. There are variations to these three equations, and they're quite straightforward. For example, if we look at this cos 2a formula, we will find a cos squared and a sine squared, and unfortunately a minus in the middle, because if it was a plus that would be just 1. But I do know that cos squared plus sine squared equals 1. That implies I can say that cos squared A is equal to 1 minus sine squared, or I can say now that's pretty straightforward. If we do either of those two substitutions into the cos 2a formula, we will get what else do we get out of this? We can just rearrange those equations, and if we rearrange them, this one, just bringing out the cos squared, and the second one, so there's no thinking at all in this. This is just a rearranging. So if it's simply a rearranging, why is it important? Well, if it was rearranging it just for the sake of it, it wouldn't be important. What is important is that you get to recognize that if you see this, it means that, or a cos squared can be replaced by it, and similarly sine squared can be replaced by this. They are necessary, and it's really important that you can see them and use them for solving of other identities that have to be proven. The issue, as I started mentioning to you guys, has to do with seeing and recognizing things that are familiar. These standard identities are, or should be, screaming out at you when you're actually playing down through a proof of an identity. So back in second year, you guys were well able to rearrange an equation, and if you remember, it was even on your junior cert, and it was only a part A of a question that say, that give you something in terms of A, B's and C's, and say, right, express D in terms of whatever it is. That's all we're doing here. Very simple. But if you mistake it and just think that that's all it is, you don't get to, in future, recognize these things in an equation. Okay, these double angle formulae, where do we use them? We will very quickly come on to the half angle formula, and they're virtually the same. You can swap from one set into the other quite easily. Instead of talking about a 2a equals something, you can say let b equal to 2a, so then you've got, instead of 2a, you've got b and a half b, so they're easily changed. But there are certain type of questions that you'll be given where the double angle formula functions for you and the half angle formula wouldn't, and vice versa. So let's look at one of the type ones where these ones work. What's the key? What should you look for? First off, we can see there are double angles in here. Okay. Now, by the way, these we're supposed to prove it's equal to tan theta. The very first thing you should notice is, unless you've got double angles, in other words, you have a theta represented someplace on its own, unless you have that, you're not going to be using double angle formula. If this was tan of 2 theta out here, you could just immediately say let alpha equal to 2 theta, and then the whole thing becomes single angles. So you have to have a double angle and an angle somewhere. The second thing is this guy. When you've got a 1, and we have another one down here, when we have that, particularly along with a cos of a 2 theta, we immediately should think of the double angle formula, not the half angle formula. Because what we want to try and do to arrive at the right hand side is we want to remove the 1's. That 1 will get cancelled. That 1 will get cancelled. We've used the double angle formula, we've gotten rid of the 1. If we had been given this left hand side expression and there wasn't a free 1 on it on the top or the bottom, you wouldn't be using the double angle formula, you'd use the half angle formula. So then what have we found now? We found that this now simplifies and we can bring out a factor. those cancel, those cancel, and yes, it's equal to tan theta, which is equal to the right hand side. That's a very short question. It's short because you made the right substitution. If you didn't, you'd be in a world of pain. You could take a page trying to solve these things. That's why practice on these basic, the usage of these basic identities in trigonometry is so important. If you practice them, these become very short and easy questions. And what it means is a section or a question on the paper that's normally considered to be a long one, and very often you'd leave towards the end. If you get good at these, you could fly through it and easily save time. It all comes down to seeing and recognizing and then making the appropriate substitutions. So one of the rules here is the double angle formulas you use when you've got a free one along with, let's say, a cos of a double angle. Yes, one last thing on these before I leave them. That expression up there could have been rewritten. Let's say you were presented with 1 plus That's clearly the same expression. What you need to recognize is that double angle formula are either going to be something like 2a and an a, or they'll be a b and a half b. In this one down here, if you don't feel comfortable using a half on an angle, all you have to do is say let alpha equal a half theta, and you sub in and you're back to something that you feel more familiar with. But there's no difference. The real issue is you have an angle and somewhere else you have double of it. If you have that, you use these. The half angle formula, which are fundamentally the same kind of thing and can be very easily proved, are actually proved by a method that you don't normally get for the Leaving Cert in mathematics, but you use a very significant number of times in applied maths. Normally when you're asked to prove something like to find this expression, that cos of 2a, which is equal to 1 minus tan squared a, I'll rewrite that, and you will say to yourself, how will I prove that? Normally what you do in maths is you will start with this side and you will play all the way down along and try and get it into this side. What you can do instead, and it's, as I said, very often what you'll do in applied maths, is you say, we've been told that this is equal to that. So why not take the more complicated one, this side, and simplify it and see if I get the other side. So what do? We have tans over here. Now, this is the reverse argument we used in solving the last problems. We know that what we have here is 1 minus and this time we're trying to get rid of the complicated bits here and here. And the usual thing is you can multiply anything by 1 and you put it in the form of the thing that's causing you the problem. That guy. So the form of 1 we'll use will be cos squared divided by cos squared. And when we multiply it across, then we'll get cos squared and we should recognize this guy. That's just 1. And we should be able to recognize this guy, because it's part of the last set that we actually proved. You will notice again, in proving this, it only requires one trick and recognize a previously established identity. So far there's been nothing complicated at all in this chapter. It's simple. When you draw the little drawings, you understand the basics of trigonometry, and you just keep observing for the identities that you're expected to know by this point in the chapter. Each of these formulae are very similar to the double angle formulae, and very often can be used to solve the same kind of problems as the double angle ones would be used to solve. One of the nice things about them, though, is that last problem we looked at, which had the free ones in it. If you didn't have a free one in it, you're better off to be using these half angle formulae. There's no sense really in deriving the remainder of them, because they're very straightforward. They're as easy as this one was. It's the principle that matters, and that principle has been applied almost without variation from the start of this talk right through to now. You will find that they're all very amenable to your own reasoning. Draw your drawings. Understand the little basic things that they're explaining to you, and just apply them. Now, I think this is a good point to make a break in this chapter, because the next stuff that we're coming on to is somewhat different, and really will rely on a lot of the stuff that we've done here. So, okay, I'll see you in a short while.